Hi, my name is Dana Golden. Welcome back to Geospatial Data Analysis in my environmental economics journey that I'm sharing with you. And today we're going to talk about analyzing geographic data. So first thing we're going to talk about is regression with geospatial data. Obviously, we're economists. We like regressions. It's the goat of our field. It's the thing we run. Most of us will never run a marathon. Most of us will never run a half marathon. We will run plenty of regressions. So a regression model what is spatial regression? Spatial regression is a regression model that accounts for spatial dependencies in the data. It's useful when the values of dependent variables are influenced by neighboring locations. So a pretty common geospatial regression is the spatial lag model. We basically have a lagged variable to capture spatial autocorrelation. So here WY is a geospatially lagged variable which accounts for the surrounding area to your particular location. You also can have a spatial error model which accounts for spatial correlation in the error term. So here you have a traditional regression, and then you have a geospatial lagged variable that's forming the autocorrelation. This is for dealing with a difference in error variance. So when you have autocorrelation, it can affect your error variance. It's less likely to affect your estimates. It will only affect your estimates if this lambda W is correlated with that X. But you definitely need to fix the autocorrelation if it exists, so you have the right set of errors, because otherwise, what are we even doing here? So how do you estimate a spatial regression in R? Use the library spdep, and then use the library spatial reg, and then you set your seed, create the data. One of these days, I'm going to actually create real data sets for this class, and it's going to be marvelous. I'm not going to rely on randomly created data sets. You find the nearest neighbors, the closest either counties or states or countries to your place of interest, maybe cities, maybe even some other feature like the closest bodies of water. You find the nearest neighbors, so this k nearest neighbors function, which you'll learn about a lot if you ever take my data science machine learning class, which will at some point exist. And then you create the weights for the nearest neighbors, which are spatial weights, which allow you to do the lags. You get your simulated data, and then you filter the spatial lag model. SLM, which is just what we're naming our spatial lag model, goes to operator, and then we use this lags ARLM, which basically is doing an autoregressive lag, but instead of a time series, we're doing it on a spatial data. You'll recall last time we talked about time series autoregression. Here we're talking about spatial autoregression. And you do your y variable, whatever your dependent variable is, and then your independent variables add to each other, and then you do data equals data, and then you do the list of weights. You do a very similar thing if you were running a regression accounting for autocorrelation in the time sense. And then if you want to fit a spatial error model, you have SEM, spatial error model, goes to, and then errors, ARLM. The only difference here is that now instead of having lags in the equation, now you're having just your lags change the error function because we're dealing with the variance. And so it's roughly the same, just changing the specification of the model, and then you do summary, and it'll provide you a summary of the results. So yeah, of course, you have a weight matrix, which is designed as spatial relationship between locations. You don't have to necessarily do k-nearest neighbors here. You can do other potential ways of figuring out what the pertinent close features are. But this is maybe just do everything within 50 miles or something. But this is what we did here. And then these are two different spatial models. This is a geospatial lag model, and this is a spatial error model. So what is spatial autocorrelation? A little bit of a more deep dive on that. It measures the degree to which a spatial variable is correlated with itself across a geographic area and indicates whether similar values occur near each other or randomly distributed. So there are very few things in geospatial data that are not correlated across space. Very few things are randomly distributed because most features kind of go together, and there's usually a continuum on a map for things like population, income, and forestry. There's just you're not, if you're in the Atacama Desert, you're not gonna walk 10 feet and then magically now you're going to be in the Arctic tundra. That's just not how that works. Yeah, this is most features have nearby locations with similar values, and then some features have nearby locations with dissimilar values. An example of this is always alternating land use patterns. Sometimes you see this kind of model with crop rotation. So how do you measure geospatial correlation and make sure it's dealt with? You use Moran's I, which is a global measure of spatial autocorrelation, or GREC, which compares the square differences in neighboring values. And you can use local indicators of spatial association, which measures the local clusters and outliers, and it tries to fit the set of locations that are similar to each other. This is more about clustering and the idea that there isn't like a fixed amount of spatial correlation across space. And then you can use this in urban planning, you can use this in environmental modeling. Most pollutants are concentrated at continuous levels and are similar across space. And of course, you can use it for public health. A lot of this was popular during COVID when you were watching the COVID spread from city to city and take a lot of lives. And then this was the Brexit map. You can notice that percent of leave is pretty spatially correlated. London on this map was very anti-leave. Well, not anti-leave, like, yeah, London, so Scotland up here, London, all the non-rural, all the very populated places, and also Scotland and Northern Ireland, both were very much in favor of not leaving the European Union. But of course, they were outvoted by the rural areas. If you do a spatial lag, this becomes very neat, because it turns out you can very well understand how a place been voted based on other places around there voted. So detecting and dealing with spatial autocorrelation, obviously, like I talked about before, global Moran's I and then local Moran's I, which can identify local clusters and outliers. And here's just the code for that in R. Moran goes to moran.test. Then you have the data of your Y variable, and then you have your weights, and then you can deal with this with the models we talked about before. You create your weighting matrix and then use a spatial lag model or spatial error model. And then finally, I'm going to talk about one of the algorithms for clustering with geospatial data. This is more of a machine learning algorithm. I'm not going to test you on this, but I think it's useful to have seen it. Clay-Beans clustering is an unsupervised algorithm that partitions data into k clusters. It minimizes the within cluster sum of squared distances. Basically, the idea of k-means is we want to make data that's close to itself, close to other data, different from the data that's further away. So we want to figure out what are the clusters in the map and what are the clusters in the geospatial object. So first off, we start off by choosing the number of clusters k, and I'll give you an example of how you can do this. You can randomly initialize k centroids, which are different points around the map that are the starting centers. It doesn't really matter what you choose, but maybe play around with this because k-means won't give you the same answers each time. You assign data to each point. You assign each data point to the nearest centroid. You update centroids to the means of assigned points, and then you repeat until convergence. So you are basically iterating until you reach a defined set of convergence with this data. And then in geospatial data, this is useful for identifying regional hotspots, grouping locations based on proximity, and resource allocation. You use geographic coordinates for clustering. Ideally, you're using other features. You're using like a bunch of geographic coordinates. Makes sense here, where like you have a bunch of discrete points, and then maybe they're clustered across space. But if you have like a bunch of states and you're trying to put states together, you want to incorporate a bunch of other features and have like a big vector of features that each state has that allows you to figure out what states it's like. So example code k-means for geospatial data. So you load in our old friend tidyverse, you load in our friend SF, you load in our acquaintance ggplot2, create your data, create your tibble. Here we have a Latin long. You have an ID here to differentiate the data points. You prepare the data for clustering. You do this little Dipler thing where you do data and then you select long and lag. You use those points. And you add cluster assignments to the data. You add the cluster assignments from k-means results. And here's how you apply that k-means. K-means underscore results equals k-means, just the function k-means built in R. Coordinates, centers equals 3. So this is the number of clusters, and then you give it a random initialized starting point, or random seed for initializing starts. And then you can visualize the clusters on your data using ggplot. So you input the data, you perform k-means clustering, and you can visualize the clusters. So there's k-means. Again, you start off with 3 things. You don't have any labeling. You just have some data, and you'd like to identify it. You'd like to put it into a different types of clusters. And here you can do that. You can also, here it is spatially with different numbers of clusters on a city. So you have clustered the city into different boroughs and regions that define how similar these are to each other. And then you can also are going to need to choose the number of clusters. So what you do is you use the elbow curve. So you start off with 1 cluster, you try 2 clusters, you try 3 cluster, and then you continue to do this until you hit the inflection point. And that's probably how many clusters you need. You also can just choose a set of clusters. This on the, by the way, this I told you I was gonna mess this up, and a lot of grad students mess this up. Learn from my example. This y-axis is the sum of squared errors. This x-axis is the number of clusters. This is decreasing in the number of clusters, and eventually it gets to a point where there's a limited decrease. Remember, it's decreasing because this is what you're minimizing. So the algorithm can always do more with the more clusters in terms of minimizing sum of squared errors, because it could always create 3 clusters and then leave all the other ones out. And it could always, in the asymptotic case, if you have every cluster's 1 data point, you have a 0 sum of squared errors. So you want to look at this. You want to look at how far this goes to minimizing sum of squared error. Ideally, you're doing this with a cross-validation data set. You've set aside some data to perform things like this, and then you test on train on one data, you cross-validate on other data. You test on one data set, and thank you. This concludes our environmental economics portion of the class. Next time, we'll be looking at our section, the second half of the class with natural resource economics. Thank you. Have a great day.